Hello everyone, welcome to College Algebra Lecture 10, and this is going to be on section 3.4 from the textbook, which is on composition of functions. So it turns out that two functions can be combined in many different ways. They can be added, subtracted, multiplied, divided, and we'll talk a little bit about that. And also you can form what's called compositions of functions. So let me first talk about the more typical ways of combining functions, and then we'll get into compositions. So two functions can be combined in different ways. They can be added, subtracted, multiplied, or divided. So here's the definition of what it means to add, subtract, multiply, and divide, to perform those operations on functions. So definitions. So if I want to add, say, a function called f to a function called g, so the way we write that is f plus g of x. Well, this is simply f of x plus g of x. So you simply add them together, right? So if these are functions in equation form, you would add the two equations together, the two functions together. If you want to subtract functions, so f minus g of x, then you simply take f of x and you subtract g of x from it. Okay, so like basically every point throughout the domain is being subtracted. If you want to multiply functions, so f times g, well, that is kind of what you would think, right? It's going to be f of x times g of x. So you multiply the two functions together. And then finally, if I want to divide, so f divided by g of x, well, that's simply going to be f of x divided by g of x. The only thing you have to be a little careful here is, remember, we can't divide by 0. So this is only true where g of x is not equal to 0. Okay, so let me give you a couple functions. Let's actually do this and see how this works out. Let's say we're given f of x is equal to x squared plus 2x, and g of x is equal to 6 minus x squared. Okay, and I want to find the sum of those two functions, the difference, the product, right, and then the quotient. Okay, so A. Let's do f plus g first. So remember, by definition, f plus g of x means f of x plus g of x. So all we have to do is add our two functions together. Well, f was x squared plus 2x, and I want to add g, which is 6 minus x squared. Now you would combine like terms. So actually it looks like the x squares cancel, right? We have 1x squared minus 1x squared. So the final result is going to be 2x plus 6. And that's it. That's the answer. So that's the sum of those two functions, f and g. Okay, what if I want to subtract? So I have f minus g of x. Well, remember, that just means f of x minus g of x by definition. So this is going to be f minus g, so be careful, put the whole thing in parentheses. Well, this is the same as x squared plus 2x. If I distribute that -1, it'll be minus 6 plus x squared. And then if I combine like terms, right, this will be 2x squared plus 2x minus 6. So that's the difference of those two particular functions. If I want to find the product, so remember, f times g of x just means f of x times g of x. Right? You multiply the two functions together. So in this case, remember the f was x squared plus 2x, and the g was 6 minus x squared. They're both polynomials. So to multiply them, I have to multiply the two polynomials together. Actually, in this case, they're both binomials, so you could also call it, just applying FOIL. But really, the way to think about this is just make sure when you multiply polynomials like this, each term in the first polynomial gets multiplied by every term in the second polynomial. So the x squared gets multiplied by both those terms, and then 2x gets multiplied by both those two terms. So if I do x squared times 6, that's 6x squared. If I do x squared times negative x squared, that's negative x. And remember, I add the exponents, right? So x to the fourth. And then I have 2x times 6, which is plus 12x. And then 2x times negative x squared is negative 2x cubed. I can't really combine like terms, right? There's no like terms in there. But let me write the final answer in descending order. So I'll write this as negative 4x. By descending order, I mean start with the highest exponent and work your way down to the constant, if there is a constant. So minus 2x cubed would be next, right? Plus 6x squared plus 12x. So that's the product of those two particular functions. And then finally, the quotient. So if I want to divide f divided by g of x, it's going to be f of x divided by g of x. Well, in this case, that's simply x squared plus 2x over 6 minus x squared. And that would be my quotient of the two particular functions. I can't really simplify it, so I'll just leave it like that. You could factor out an x from the numerator, but you don't need to, so that's fine. Okay, so that's the basic idea of adding, subtracting, multiplying, and dividing functions. Now, another way that we can combine functions is called a composition. All right, so let's talk about that next. So a composition. So composition of functions. So when the output of one function is used as the input of another, we call this a composition of functions. And the way that we write that is with a little central circle there. So f and that little circle g, the way you read this is f composed with g. So f composed with g. Okay, and then the way you should interpret this, so f composed with g of x means f of g of x. So think of it now, g of x is sort of like the input to the f function, right? The outside function is the f function, and g of x is the inside function. It's the input to that outside function. Now, in terms of the domain of a composite function f of g is all x such that x is in the domain of g and g of x is in the domain of f. Okay, we're not going to spend too much time on domain of composition of functions, but I'll do one problem later and explain how that works. It's a little tricky when you're talking about compositions. All right, so compositions in general. Let's do some examples. Let's say we let f of x equal 2x plus 2 and g of x equal 5x squared plus 4x. And I want to find f of g of x. So I want to find the composition of those two functions. Okay, so remember what that means. It means f of g of x. So g becomes the input to the f function. So I look at my outside function, my f function, and where I have an x, I'm going to plug in g of x. Right, so I looked at my outside function, the f function, and where I had an x, I plug in the entire expression for g of x. Okay, and then, of course, you would simplify this, so I can distribute the 2. So this would be 10x squared plus 8x plus 2, and that would be the answer. Okay, we can also think about this, well, there's many different ways. Just like with anything with functions, we can think about equations, like formulas, right? Like we're doing right now, equations. We can think about functions in terms of graphs, functions in terms of tables. So let's do a couple of examples like that where we look at compositions in terms of graphs and tables. So let's say I have these two graphs. So let's go 0 through 6. Actually, I'll pause it for a second and complete these graphs. Okay, so there are my two graphs. I have a graph of the function f on the left and a graph of the function g on the right. So given those graphs, I want to find these compositions. I want f composed with g evaluated at 5, then g composed with f evaluated at 0, f composed with itself, f evaluated at 6, g composed with g evaluated at 3. So let's do the first one over here. I'll do the f composed with g, so f of g of 5. So I need to figure out what the inside value is first, right? What is g of 5? So I go to my g function, g graph, I go to 5, go up, read off the value. Well, it's also 5. So this really is the same now as f of 5, right? Because we just found that g of 5 is simply equal to 5. And now I can go to my f function And if I look at f of 5, the output is 0. So this is equal to 0. Okay, what about g of f of 0? So now I go to the f function first. It's my inside function, so I go to f. Well, what's f of 0? Well, if the input is 0, the output is also 0. So this is the same as g of 0. Now I go to my g function, and if the input is 0, the output looks like it's 2. So this should be 2. So g of f of 0 is equal to 2. What about f of 6? So I go to my inside function, right? F and evaluate it at 6. So if the input is 6, the output of f is 2. So this is the same as f of 2. So I now go back to my f function, and if the input is 2, what's the output? It looks like it's 1. So this is equal to 1. And then g of 3. So I go to my g function, it's the inside function. At 3, if the input's 3, the output is 4. So this is the same as g of 4. Then I go back to the g function, right? And if the input is 4, the output is 2. So this is equal to 2. Okay, so one function becomes the input to another function, right? That's the whole idea of a composition. All right, let's do an example with a table. Let's say, here, I'll do a new page here. Again, I'll pause it and draw the table, and then we'll talk about the example. Okay, so I have a table where my input values are the first row, so the x values are my input values. Then I have the function f, which is the second row, and the function g is the last row, right? And those are my output values for each of those particular input values of x. And I want to find f of g at -1, g of f evaluated at 5, f of f evaluated at 7, and g of g evaluated at 2. Okay, so first of all, remember what this means. F of g -1 is the same as f of g at -1. So we go to our inside function, the g function. If the input is -1, that's here, what is the output of the g function? It's -3, right? So this is going to be the same as f of -3. So now I go to my f function, and where the input is -3, the output is a +1. So this should be equal to 1. Okay, second one, I want g of f 5. So again, you can write it, it makes more sense to write it this way, g of f of 5. So I go to my inside function, which is the f function now. The input is 5. So the input is 5. What's the output of the f function? It's -4, right? So that -4 now becomes the input to the g function, to the outside function, right? This was just -4. So now it's the input to the outside function, which is now my g function. So I go to my g function. If the input is a -4, what's the output? It also happens to be -4, right? So in this case, the answer is going to be -4. If I want f of f at 7, well, this means f of 7. So I go to my inside function, which is f. If the input is 7, the output is 2, right? So this is the same thing now as f of 2. So 2 becomes the input to f again. So again, I go to the f function. If my input is 2, the output is -3. So this is going to be -3. And then finally, if I want g composed with g evaluated at 2, this really means g of 2. I go to my inside function, which is g. If the input to it is 2, the output is also happens to be 2. So this is the same as g of 2. And then again, if the input is 2, the output is 2. So I guess the answer is going to be 2 in this case. Okay, so it's just composition of functions, but now using a table instead of a graph or instead of a formula or an equation. Okay, now of course you can compose more than 2 functions. Like, for example, let's say I have f of x is x to the 4th plus 3. Say g of x is x minus 6. And h of x is the square root of x. And I want to find f of g of h of x. Okay, so the inside function is my h, right? That first has to be the input to the g function, right? So let's find g of h of x first. So now I go to the g function, and the input, wherever I have an x, I'm going to stick in h. So in this case, it's going to be square root of x, right? That's where I have an x. I'm going to stick in my h expression. So that becomes square root of x minus 6. Then I take that, the g of h of x, and I plug it into the f function. So now f of g of h of x is going to be square root of x minus 6. That's all raised to the 4th power plus 3. Okay, and you could expand it out. It's kind of a mess in this case. I'll just leave it like that. So that would be f of g of h of x. Okay, another example. Let's say I have f of x is equal to the square root of x squared plus 6x plus 10. And let's say I have g of x is equal to negative 9x minus 2. Okay, and I want to find f composed with g of x, which remember just means it's f of g of x. So I go to my outside function, which is the f function, and where I have an x, I'm going to plug in g, right? So this is going to be the square root. Now where I have an x, I have to plug in g, but I need to square that, right? Plus 6 times that quantity again, plus 10. Now again, you could just leave your answer like that, or if we want to simplify this or expand it out, I need to do underneath the radical first. So let me actually square that first term. So remember, this means negative 9x minus 2 times itself. So I need to FOIL it out. Right, so this is going to be 81x squared. Then I have plus 18x plus another 18x, so plus 36x. And then negative 2 times negative 2 is plus 4. Okay, so if I plug that in, I have 81x squared plus 36x plus 4. And then I can also, I guess, distribute this 6, right? So this is going to be negative 54x minus 12 plus 10. And then if you simplify all of that, you're going to get square root of 81x squared. 36x minus 54 is negative 18, so negative 18x. And if I combine the constants, I have positive 4 minus 12 plus 10. That's going to be a positive 2. So that would be my answer. So f of g of x, in this case, is equal to the square root of 81x squared minus 18x plus 2. What if I wanted to find, so using the same functions, so remember f of x was square root of x squared plus 6x plus 10, and then g of x was negative 9x minus 2. Okay, so in general, we found f of g of x, right? Which is true for any input x. And we found it to be the square root of 81x squared minus 18x plus 2. What if I wanted to find f of g of 1? Well, since I did all that work, right, to find f of g of x for any input x, then what I can do is just go to that expression and where I have an x substitute in a 1, right? So this will just be 81 times 1 squared minus 18 times 1 plus 2. But this is the same as 81 times 1, which is 81, right? Minus 18 plus 2. And that turns out to be the square root of 65. Okay? And that's fine. If you have the general equation in terms of any input x, then you could just substitute in that value. Now, what if we didn't go and do all the work for this step first? How would I find f of g of 1? Well, it might be simpler, right? Just to find g of 1 by itself. So if you go to the g function, where I have an x, I'm going to plug in a 1. So that's going to be negative 11. And then now that becomes the input, right? So f of g of 1. That becomes the input, negative 11, to the f function. So now I go to the f function, and where I have an x, I'm going to plug in negative 11. So it's negative 11 squared. And then it was plus 6 times negative 11, and then plus 10. And then if I simplify that, so this is what, 121 minus 66 plus 10. And if you worked it out, of course, you're going to get the same thing. It's the square root of 65. So if you already have the general equation for any input x, if you already have this one, then it's easy just to plug in, right, for that value. But if you're given those two initial functions and you're asked to find this immediately, right, just one particular composition at one particular input, it's probably easier to do it this way than to find the general expression. It just depends on how complicated it is. Okay, what about this? Let's say you're told that f of x, suppose f of x is 1 over minus 5x plus 6, and g of x is 1 over x squared plus 2x plus 7, and we want to find f of g of x. So I go to my f function, right, and where I have an x, I'm going to plug in g of x. So that x becomes the entire function g, so I have to plug in the entire expression on the right-hand side. And that's it, right? That would be my answer. Now, of course, you could simplify this, right? You could multiply, you could clean up the fact that it's a complex rational expression and clean this all up. In most cases, MyOpenMath will accept that, so you don't need to always clean it up. But sometimes it'll ask you to write it in simplest forms or, expanded form. So you have to be careful. But in many cases, you could just put that in as your answer, and that will be correct. All right, so for now, I'll just leave that as a correct answer. Okay, I promised I would do one question on domain. So let's talk a little bit about that. So let's say I'm given f of x, I'll call it h of x. H of x is 1 over square root of x, and m of x is x squared minus 4. Okay? So let's see if we can answer this question. Let's see if we can find the domain of h of x divided by m of x of h of m of x, so that composition, and then we'll do it the other way, m of h of x. Okay, so I'm going to go to a new page. First of all, let's find h of x over m of x. Well, remember the h function was 1 over the square root of x, and the m function was x squared minus 4. That's 4. So if you want, you can think of this, if you want to think of this as a fraction over 1, right? Then it's the top fraction times the reciprocal of the bottom fraction. So really all it does is it puts the radical x in the denominator. I'll write it like this. Okay, so that is the quotient of h and m, right? Those two functions. Now, what is the domain? Well, there's several restrictions, right? Because of the square root, we know that x has to be greater than or equal to 0. And because it's in the denominator, it can't even be 0, right? So I know that x has to be greater than 0, right? And that comes from, that restriction comes from the 1 over square root of x, right? It's in the denominator, so it can't be 0. And then because it's under the square root, it has to be positive. So x has to be greater than 0. The other restriction comes from the denominator, right? The other piece of the denominator. I know that x squared minus 4 can't equal 0, right? Because I can't divide by 0. So square root of x can't be 0, x squared minus 4 can't be 0, and because it's the square root of x, x has to be positive. Okay, so how do I figure out what values x can't be? Well, if x squared minus 4 can't be 0, let me set it equal to 0 and solve. Right? Let me figure out what makes that expression equal to 0. So how would I solve this? Well, there's a couple different ways. In this case, it's really easy to factor it. In fact, it's just a difference of squares. So this is x plus 2 times x minus 2. So one solution is x plus 2 equals 0. So that's going to give you the solution x equals negative 2. And the other one is x minus 2 equals 0. So that's going to give you the solution x equals positive 2. Okay? And then we already know from this restriction, from the square root, that x has to be greater than 0. So I know several things now. X has to be greater than 0. x cannot equal positive 2 or negative 2. Well, I don't have to worry about that one, right? Because I know it has to be greater than 0, so that eliminates a negative 2 anyways. It definitely can't be. But it also can't be positive 2. So how do I write this out? Well, the domain, and we'll do this in interval notation, is going to go from 0, but not including, right, because it can't be equal to 0, all the way to 2, but not including 2, union 2 to infinity. So that would be the domain of that quotient, right, h divided by m. Okay, what about the second one, which was a composition? It was h of m of x. Okay, so let's figure out what this composition is. So I go to the h function, the outside function, and where I have an x, I'm going to plug in m. And m in this case was x squared minus 4. Okay, so now let's figure out the domain. Well, if you look at this, my restriction, right, do our restrictions, are that x squared minus 4 has to be non-negative, and because it's in the denominator, it cannot even be 0, right? Because the square root of 0 gives you 0, and we can't divide by 0. So what we're saying is that expression must be greater than, strictly greater than 0. Okay? So how do we figure out where, in this case, a quadratic, we have like a quadratic inequality. How do we figure out for what x values x squared minus 4 is greater than 0? Basically, the way you do this is you set it equal to 0 first, and you solve it. And we already know the solution to this, right? This is going to be, if I factor, it's x plus 2, x minus 2. So it's going to lead to the solutions x equals negative 2 and positive 2. Then you make a table. So I make a little table here. So this is where negative 2 would be. This is positive 2. And I'm going to look at all of the x values in the 3 intervals. Before negative 2, between negative 2 and positive 2, and then greater than positive 2. Okay, and I want to see where, for which interval, do I get a true statement when I plug it back into that inequality. So at this case right here, this interval, this is where x is less than negative 2. Here is where x is greater than negative 2 and less than positive 2. And here x is greater than positive 2. So what you do to figure this out is you pick test points in those intervals. So test points. So what's a nice easy value to plug in where x is less than negative 2? Maybe like negative 3, right? It'd be nice easy to plug in. What about between negative 2 and 2? Maybe x is 0. 0 is always easy to plug in. And in greater than 2, maybe positive 3. So if I plug in negative 3, right? So I have this, by the way, we can write this as, I can write the actual inequality as x plus 2 times x minus 2 is greater than 0, right? So let's plug in negative 3. So I have negative 3 plus 2 times negative 3 minus 2. Well, this is negative 1 times negative 5. What's negative 1 times negative 5? That's positive 5. Right? So is that greater than 0? Is positive 5 greater than 0? Yes. So here we have true. So if x is less than negative 2, it satisfies that inequality. Right? It makes it true. Now try 0. Well, I plug in 0. I have 0 plus 2 times 0 minus 2 is greater than 0. Well, this is 2 times negative 2. That's negative 4. Is negative 4 greater than 0? No, that's false. Then I'll try 3. So I have 3 plus 2 times 3 minus 2. Is that greater than 0? Well, this is 5 times 1, which is 5. Is that greater than 0? Yep, that's true. So the interval where it's true is when x is less than negative 2 and when x is greater than positive 2. Okay, so if you go back to our composition here, h of m of x, the domain is going to be where x is less than negative 2 and where x is greater than positive 2. So how do we write that in interval notation? It would be from negative infinity to negative 2 union to infinity. And you have to be a little careful. I need to look at one more thing. I need to go to the m function, right? So I'll also say look at m function for any additional restrictions. Well, remember the m function is m is equal to x squared minus 4. Are there any issues with any of those inputs for x? No, right? Its domain is the entire, it's all real numbers from negative infinity to positive infinity. So there's no additional restrictions, right? So I'll say there's none. There's no additional restrictions. So this is the correct domain. Sometimes you have to fix this a little bit if there's any additional restrictions. Because remember, m is the input to h. So if there's already some problems with m, then it doesn't make sense, right? Like if you're dividing by 0 at some point and you plug it into h, you have to be careful. You have to recognize that you can't divide m by 0. So you have to look to see if there's any additional restrictions. This is tricky. I understand. We're not going to spend too much time on domains of compositions, but I figured I would just do one example. Okay, we have one more piece, one more part to look at. So here, now we want m of h of x. So now I go to my m function, right, which was x squared minus 4, and where I have x, I'm going to plug in h, which is 1 over square root of x. Okay, now, of course, if we square that, of course, this is going to be, think of this means 1 over square root of x squared means 1 over square root of x times itself, which is equal to 1 over x. So this is 1 over x minus 4. And it looks like, right, it looks like the only problem is going to be x can't be 0, right? Because we can't divide by 0. So you could say x can't be 0. And then that would mean the domain is going to be from negative infinity to 0, union 0 to infinity, right? The only value can't be a 0. But here's where you have to be careful. So again, we have to look to see if there's any additional restrictions on the h function. Well, what is the domain of the h function? Remember, that's h. Well, since I can't divide by 0, and I'm also taking the square root, this is saying that x must be greater than 0. Right? So now I want to put these together. I want to put this together with any additional restrictions, and you're going to find that the domain, think of it as where these two would overlap. the domain is going to be just from 0 to infinity. Okay? Because we simplified it, we got 1 over, right? When we simplified it, we got 1 over x minus 4. But if you go to back to the original function, x can't be negative, right? Because if x were a negative 5 or something, square root of negative 5 is not a real number. We're not dealing with complex numbers or imaginary numbers in this particular case. We're just talking about real numbers. So that can't be a real number. So therefore, m of h of x wouldn't be correct if x were less than or equal to 0. So the domain is going to be just when x is strictly greater than 0, right? So from 0 to infinity. Again, I know that it's one of the harder concepts, is this domain of compositions. So we're just going to touch upon it a little bit. Okay, one last quick thing before I end this section. Let's say you're told, let's like work backwards now. Let's say you're told the function h of x equals 1 over x plus 5 can be expressed in the form f of g of x, where g of x is equal to x plus 5, and f of x is equal to what? So what does f of x have to be if we want to get a composition, which we're calling h, right? So h of x is really the composition of f of g of x. So if we're saying that g of x is x plus 5, what does f have to be so that when I do that composition, I get my h here? Well, if you think about it, f of x must just be 1 over x, right? Because then it's saying where I have an x in my f function, I would plug in my g, plug in my x plus 5. So right here, I'd plug in x plus 5, and I would get my h, right? I get my composition. All right, let's do one more of those. Let's say the function h of x is equal to x plus 4 to the 6th can be expressed in the form f of g of x where f of x is equal to x to the 6th and g of x is equal to what? So again, think about it, right? We want a composition, which we're calling h, which is equal to f of g of x. And I know my composition has to be x plus 4 to the 6th. And I'm saying I want my outside function to be x squared. Oh, x to the 6th. I'm sorry, I wrote that down wrong. Could do x squared too, but let's do x to the 6th. So f of x is x to the 6th. What must g of x be so that I get h, which is x plus 4 to the 6th? Okay, so g is the inside function, right? So what would I plug into f to end up with h? Well, g must be simply x plus 4, right? Because if I substitute that in for the x there, then I'm going to get my h function. I'm going to get x plus 4 to the 6th power. Okay, great. So that's it for this section. And next time, we're going to jump ahead a little bit. Next time, we're going to talk about the last section in chapter 3, which is on inverse functions. Okay, so we'll do 3.7 is one more section we need to do for chapter 3. Great, thanks.